Hello, everyone. Thank you so much for joining us today. I know it's super late in the evening, so really appreciate you all coming out here. My name is Anam Jangshe. I'm a product manager on Aurora team with AWS. And today, joining me here is Peter.
Hi, my name is Peter Fine. I'm a software engineer at VMware. I actually started working on the Cloud Hub platform in 2016. We've been on quite a scalability journey, and happy to be here.
So today, we are going to talk about how you can build scalable multi-tenant databases with Amazon Aurora. We're going to deep dive into multi-tenant design patterns. We'll talk about different key capabilities that Aurora provide to help you design multi-tenant databases. And then we'll talk about how Aurora enabled VMware to consolidate their 166 self-managed MySQL databases to just 92 Aurora clusters, and how they achieved cost and operational efficiency along the way. So let's get started. First, what is Aurora? It is a fully managed MySQL and Postgres-compatible relational database that is built for the cloud. You get the performance and availability that you expect from a commercial database, but at just 1/10 the cost. And we also have the distinction of being the fastest growing service in the history of AWS. Now, when you're designing your databases for multi-tenancy, there are various factors that you have to keep in mind. So the first one, isolation. How do you keep your tenant data separate from one another? Another factor that you have to think about is scale. How many tenants are you going to have? What is going to be their storage requirement? What kind of workload do they see? Is it a constant pattern? Do you see spiky behavior? Is it unpredictable? And what kind of cost that you want to spend on your solution? So not just the overall cost, but cost per tenant as well. So depending on which design pattern you pick, your costs can vary drastically. The fourth one is the operational complexity that you're willing to handle. So for example, you have to redistribute tenants. How are you going to do that? How are you going to monitor your entire solution, as well as individual tenants as well? So what we're going to do is we're going to talk about each of these key themes and tell you about how Aurora can help you in all these different aspects. So let's talk about isolation first. So if you want to have the highest level of isolation, what you want to do is put a single customer or tenant on a single cluster. So this gives you the highest degree of isolation because your tenants are not going to be sharing any of the resources. But now, if you are thinking about your customer base, which is hundreds and thousands of customers, which is typical for a SaaS scenario, this may not be a feasible solution. So what you end up doing is you pack your customers together, your tenants, into multi-tenant clusters. So this way, you can get better utilization and improve your cost as well. And for this pattern, there are various isolation levels that you can get. You can pack all your tenants in a single schema, where you are isolating them at table level. You can use features like row-level security that's available in Postgres. So for each of the tenant, they can only view the rows that are associated with them. Another level you can do is you can isolate customers at schema or database level. So customers can only view the schemas that are relevant to them. This gives you higher level of isolation than compared to single schema. Now, isolation was the first one that I mentioned. Let's talk about scale. So we have introduced a lot of innovation across the entire architecture of Aurora to help you scale up and down for your multi-tenant workload. Now, one of the key components is separation of storage and compute. So if you're doing any routine operation, for example, let's say you're running backup, you don't have to go wake up compute. You can do that in the storage layer. So let's talk about the storage layer. So this is a purpose-built, log-structured distributed storage that's designed for the cloud. It's spread across 3 availability zones. Always, always. You don't have to do anything. We maintain 6 copies of your data across these 3 availability zones. So now let's say something happens with a node, or the whole availability zone goes down. It has 0 impact on your availability of the application because you still have those other 4 copies of data. So this is how we claim high availability, durability, and performance for Aurora. Now, we store your data in 10 GB segments. So as your application grows, you're getting more and more customers, the storage layer will automatically scale up to accommodate that. And now if you're redistributing tenants or your tenants are leaving because they're coming to the end of their life cycle and your data size shrinks, the storage layer, more importantly, will also shrink with it. So you're only paying for the size that you're using and nothing more. Now, let's come to the compute side. If you have a single AZ deployment, that means you have a single node, that's your writer, that connects to the storage layer with the intent to read and write. With the separation of storage and compute, you can scale your compute layer independently. Now, you scale the storage. How do you scale compute? Aurora gives you the capability to add up to 16 low latency read replicas. Now, if you're only going to create one, make sure to create it in a separate AZ so it can also act as a failover target for you. So here in the architecture, you see how you can scale storage up and down. Aurora takes care of that for you. For compute, you can scale it vertically to bigger instances as well as horizontally as well by adding more readers. Now, what if your tenants are spread all across the globe and you want to serve them closer to where they're at? And in this scenario, you also don't want to have a dependency on a single region. So if you're packing lots and lots of tenants together in a couple of clusters, you want to make sure you're not dependent on single regions. So if something goes wrong, you need to have other regions available to take over. In this case, you can use Aurora Global Databases, which gives you the capability to span your cluster across different regions. So it gives you a low latency read scalability across these regions with typically a lag of less than 1 second. Aurora gives you the capability to create up to 5 secondary regions. So in total, you get 90 readers. Now, you can be in a situation where you want to do writes to your application from across these different secondary regions that you have. So Aurora gives you the capability of write forwarding, which sends occasional writes from the secondary region to your primary region. This feature is available for Aurora MySQL. Now, in addition to all of these benefits, of course, you have a disaster recovery solution as well. So in case something happens to your primary, the secondary can take over. Now, we talked about scaling storage, compute within region, across region. What about your connections? So in a multi-tenant solution in SaaS, you'll be keeping a lot of connections open to get a quicker response time. It's a typical behavior that we see across our customers. Most of these connections might be idling most of the time, but your database is still handling them. You're using your precious database resources to manage these connections. And you want to make sure that you preserve these resources. You want to use these resources for the actual work they're supposed to do, to run your queries, your transactions. In this case, what you can do is use Amazon RDS Proxy, which is a fully managed, highly available database proxy that you can place between your application layer and your database layer. And it helps you scale your application by pooling and sharing database connections. Now, in addition to that, RDS Proxy also helps you with availability. It reduces failover time by 66%, and it also improves security by integrating with AWS Secrets Manager and AWS Identity and Access Management authentication. Now, let's go back to our different models that we were talking about. So in an ideal world, you want to put everybody, all your tenants, into a single tenant per cluster because you want to get that isolation benefit. But if you're talking about the scale that you're operating at, you have hundreds and thousands of customers. Creating a database for every single one of them is not feasible for the scale that you're operating at. It's going to be very costly because most of the time, the full capacity is not going to be utilized. And then having to manage these databases individually is a pretty challenging task. So in this scenario, you start packing together your tenants into a multi-tenant cluster. Now, of course, you're going to get better utilization out of that. You're going to improve your cost. And to be most efficient, what you can do is pick the biggest instance size you can find, pack as many customers as you want. But there's a challenge there. You can't tune to the needs of specific tenants that you have. You can't do any of that. So any operation then, if you have to do, you have to think about all the tenants that are in that cluster. So if everybody's in there, you're going to think twice before touching that cluster. So now, where you want to land up is somewhere in the middle. You want to get the benefit of single tenant in a cluster, as well as having multiple tenant in the cluster so you can improve your utilization and the cost. So this is where you want to end up in. Now, independent of how you distribute your tenants in this mixed mode, you don't want to be handling capacity manually. Because if you end up with insufficient capacity, your application is going to experience degradation. But on the other side, if you are always provisioning for peak capacity, that's a very expensive solution, and you're not using that capacity most of the time. You're only paying for it. So what you end up doing is you're continuously monitoring it, and then you're scaling it up and down when the need comes. Not only is this challenging, but it requires downtime. So this is not desirable. So this is where Aurora Serverless v2 comes in, which is an auto-scaling configuration for Amazon Aurora. What it does is it scales automatically between a minimum and a maximum capacity that you configure. We measure capacity in ACUs. So to give you an idea, one ACU is equivalent to 2 GB of memory. And the CPU and networking that you get is similar to what you get on provision instances. Now, we also scale in fine-grained increments, so we make sure that the database scaling mechanism, it closely follows your workload. So you're not over-provisioning at any point, and you're only paying for what you're using. We've reduced the size of the smallest database that you can have. The smallest that we support is 0.5 ACUs, so it's a pretty tiny database. So with serverless, you can put more and more of your tenants in single tenant per cluster and get the benefit of the isolation. And if you're operating at the scale of hundreds and thousands of customers where you have a long tail where most of the time your tenant would be idling, you can pack all of those tenants together in the cluster. Now, to minimize the impact that these tenants have on each other, you want to make sure that you minimize the number of tenants that you're packing together. And serverless allows you to do that. So minimize the number of tenants that you have on the clusters so serverless can still handle at minimum capacity that we offer when these customers are idling. And when they need database capacity, the instance will scale up to support that workload. Now, here I talked about how serverless helps you with scale. It helps you with costs because your database scales down when you don't need that capacity. And you're not managing the scaling manually. It's all done automatically, so it simplifies some of your operational workload. Now, you must be thinking, sure, we get all these benefits, but how does it work under the hood? So with Aurora Serverless, we scale by what we call in-place scaling. We take a running database process, we give it more resources that it needs. We give it more CPU, we give it more memory. So whatever resources that it requires, we give it to the running database process to scale it. To think about the factors that we look at to scale the database is CPU, memory. We look at the pressure on the internal structure, your buffer pool, to see if it requires more resources. The third factor we look at is network throughput. So anytime your application requires these resources, we scale up the database so your workload gets these resources. Now, we're not just looking at the foreground processes, so the queries that you're running, we're also looking at the background processes as well. So if we need resources for that, the database will scale up to adjust. Now, another thing to keep in mind is that the scaling rate is predictable. It is not constant. It varies. So the bigger the database, the faster the scaling rates you get. Now, this is how serverless can help you scale automatically based on your application needs. It also reduces costs because it scales down when there is no workload on it, and it simplifies your operational complexity. Now, you can still run into situations where you may need to move tenants around still. So your tenants are evolving, the requirement changes, it grows, some will start getting spiky behavior, patterns change. So in those cases, you want to redistribute your tenants to rebalance workload across the different clusters that you have. Now, let's say if you do a snapshot and you want to restore it, it's going to be a very time-consuming operation because it's dependent on the size of the data. Now, if you're talking terabytes and terabytes of data, you have to wait for all of that to finish. So how does Aurora help here? What you can do is use fast database clones. Now, what is a clone? It looks like just a regular Aurora cluster, but it points to the original data pages. So the clone that we create is going to be pointing to the same source storage layer. We do not make copy of the storage layer, so you can get a clone in a couple of minutes. And another interesting point, so for your scenario, now, once you've made the clone, you want to remove the tenants that you don't need in that clone. You can just make the change. The source cluster doesn't even know what's going on. You can make the change, and you're only paying for this change data. So you're saving costs there as well. And now you can continue using your source cluster. You can continue making changes on that, and it'll point to those changes. And the clone doesn't know anything about it. Now, another thing I mentioned was that we're not making copies of data, so you're not paying additionally for all these copies. You're only paying for this change data. Now, another thing to think about is monitoring. So how do you simplify your operational workload in terms of monitoring? What is happening across your entire solution? Now, Aurora gives you various capabilities to help in that aspect. So if you want to look at instance level, you can look at CloudWatch metrics. So for example, with Serverless v2, you can look at CPU utilization, how much CPU is being consumed by your system. You can look at freeable memory. That gives you insight into what is going on the system. If you want to go one layer deeper to look at what is happening with the operating system, you can look at Amazon RDS Enhanced Monitoring, which gives you that insight. We also provide support for Amazon RDS Performance Insights, which is a simple yet powerful dashboarding experience that we provide, which can help you look at performance bottlenecks, for example. And the last one I want to talk about is Amazon DevOps Guru, which is a machine learning-powered capability to help you detect and diagnose your operational issues and performance issues. So these are some of the key capabilities that Aurora provides that can help you monitor your entire fleet, look at what's happening with the databases, which are the queries causing problems. Now, so far, I've only talked about how Aurora helps you with isolation. It helps you with cost, scale, and operational complexity. Now, let's talk about how Aurora enabled one of our customers, VMware, and go into details about their real-life experience of moving their multi-tenant workload to Aurora and the benefits that they gained on the way. So Peter, all yours.
Thank you, Anu. Thank you. Okay, so just to set some context, some of you might be familiar with Cloud Health, the cloud management platform we were acquired by VMware in 2018. So these databases are primary databases powering this platform. So for those of you not familiar, what we do is our customers give us access to their clouds. We pull in a huge amount of data from APIs, billing data, ingest it into the platform, run it through all sorts of data pipelines, and we have all sorts of layered features for reporting, financial analysis, governance, optimization, all sorts of stuff. So the company was founded in 2012. This is a true SaaS, web and API-based application born on AWS, currently about 20,000 customers, and some data sizes, we have about 45 terabytes in relational, about 45 petabytes in S3. I think we process about 1.2 billion cloud assets a day. So this is what these databases are powering. So kind of where do we get started? So it's founded in 2012. It was originally Ruby on Rails. And at that time, MySQL 5.6 on EC2 was the best we were going to do. We said the main database. And over time, we're building out a very wide set of applications, front-end, back-end processing. It's a very mixed load. And we're building a lot of features. And over time, we're just continuing on this homegrown architecture. These are chef-managed instances. We figure we're supporting about 200 customers on a single database or a single schema. So this is true multi-tenant, where data is co-located, and it's chef-managed. really just general improvements over time as we build out this big farm of databases. We did add some bin log replicas, really just for failover only. They're just kind of sitting there, and as I said, I started in about 2016. We had maybe 6. 4 years later, we have 166, and we're talking pretty big instances, and it's time, it's becoming a challenge, and we need to look for new architecture. But I want to talk a little bit just about the multi-tenant pattern, as I said. So we co-locate data on our schemas or MySQL databases. The original model was one schema on MySQL database. So as we looked at this migration, we saw a great opportunity to consolidate those onto Aurora clusters. We were 3-to-1. So this was kind of the model we were looking at. We do have some large customers that have their own schema, just a handful in general. As I said, we have hundreds of customers co-located on a single database. Oops. And just a little bit more multi-tenant data management. There's a lot of factors. We're talking about customer data, customer shard, but how do you kind of manage schema changes? How do you manage like reference data? We've been working on this system for a while, kind of have the concept of a root database or like a DB1 that contains all reference data that's used to generate unique IDs across the platform. That all gets replicated. As I said, we built a lot of homegrown tools to manage a system like this. Set proper context for shard and customer for any type of operation in the platform, tools to do things like data mining across the cluster. And I will say, as we got into this migration, we did not require any changes for Aurora. So what were the challenges? So we have this big group of homegrown MySQL databases, this community MySQL 5.6. We're on an outdated release. We have these single databases. Our entire application ecosystem is connecting to them, and we're running the scalability issues. We're exceeding connection limits, we're overloading CPU, and we're creating, as we'd say, there's a lot of fire. We're putting out a lot of fires all the time. We're failing over to those replicas, trying to upsize. It started becoming a real issue for our operations. We're also running those replicas, and we're continuously over-provisioning to cover peaks. And we have a lot of resources sitting idle, so we're kind of wasting money. And then, of course, the human impact. We had 2 full-time DevOps resources just running those community MySQL, that farm, not really doing anything else. Plus, the issues we're having kind of filter down to development teams, hold up deploys, just create a lot of impact across our organization. So what were our goals? So we had looked at Aurora a while back. It kind of took us a while to get to the point where we're ready just to start this project. We're going to migrate those. It was 166, but it was really 332 because of the replicas. And we're going to simplify our operations and support the multi-tenant growth. We're taking on a huge amount of customers, and we're growing. The tenant sizes are growing. Growing rapidly, so it's kind of a 2-direction scaling problem. We want to obviously improve the performance, reliability, and try to stabilize our costs and not have underutilized resources. Kind of what were the alternatives for us? I mean, we did talk about continuing to maintain a homegrown architecture. We could have upgraded to like a MariaDB or Percona. Roll your own clusters, roll your own proxy SQL. We were really looking to move to a cloud-managed database. So how does a project like this sort of go down on a timeline? This was a 1-year project for us. All of 2021 occupied all my time. And kind of looking back, this is how I kind of broke it down. We started off in January with kind of research and proof of concept, performance benchmarking. We got a lot of support from AWS on this project, got some deep dives and some training. We started migrating in the early spring. We were able to, because Aurora's got great compatibility with MySQL 5.6, we were able to put Aurora Shard into our pool as kind of a soft launch, run some internal tenants, and we're building out various tooling and provisioning for kind of a larger scale effort. We did start to migrate some of our customer shards. We did run some issues. It wasn't always rosy. We had some performance issues, some connection management issues, and we did pause for a little bit in the summer. We said we got some deep support from AWS. We got some things fixed in both Aurora and in RDS Proxy. We used that time also to work on modifying our applications to take advantage of Aurora clustering. And really, as we came out of that summer, we were in very good shape. We had fixed all the issues, and we got into kind of the fourth quarter of that year was really a bulk migration phase. We fully automated this process. We started getting to kind of the cost side, buying RIs. The application optimization for Aurora has been an ongoing process for us, and at the end of the year, we were done. We had shut off all of the EC2, and it was a really big milestone for us. I want to talk a little bit of the mechanics of how you actually think about cutting over from homegrown MySQL to Aurora. So the compatibility was fantastic with 5.6. So we were able to use normal tools, MySQL dump, MySQL load, to bring schemas over off of the EC2 into Aurora, including the consolidation process. And then set up standard type bin log replication between MySQL 5.6 and Aurora. And when everything was caught up and we were ready, we had a script that would just flip our DNS over to Aurora. And this was basically a hot cut over. With very little platform downtime, maybe a few read-only error blips, but we did not take our platform down for this migration at all. Once we really got that process locked in, this became just, we were doing this bulk, a whole bunch every day, and it went quite smooth. So we finished this project, and I'll talk a little bit about kind of Aurora features and how they work very well for us. So Anoop talked about the storage model. If you're coming from an EBS or EC2 solution, you're managing your own storage databases. So Aurora manages it for you. That cluster limit gives us a huge amount of headroom. And we're only paying now for the storage we use. And as I said, all the expensive operations that we'd have to do for EBS management and upsizing just went away. So this chart shows kind of all of our cluster storage kind of imposed on a single chart here. The interesting thing is that the top line is actually our largest tenant. It is a single tenant cluster, is I think now about 3.5 terabytes. So when you think about kind of multi-tenant management, you may have some tenants that are so large they exceed the storage of thousands of smaller tenants. Really makes for some very interesting scaling challenges across the platform. So talk a little bit about the reader read node. So this was a big point for us with Aurora coming just from single MySQL instances. All of a sudden with Aurora, you get instant clustering with the reader nodes. So as I said, we're slowly modifying our applications. We have a lot of very read-intensive applications, a big reporting platform. So a lot of code that we could easily kind of block over to start to use the reader nodes. And in time, it was very nice watching our reader load kind of go up, writer load go down, and we just got into some very basic scaling. Our scaling patterns are now really able to take advantage of Aurora scaling patterns, and Aurora has some advanced scaling patterns. But for us, it's very simple now. If we are exceeding our reader load, we can just add a reader onto the cluster, and if we need more horsepower because of larger tenants, a bigger writer load, we will just do an upsize operation. So very simple horizontal and vertical scaling. This is done no downtime at all. So it's a huge difference from trying to upsize EC2 instances and doing kind of a dump and load and cut over. This is it's just night and day. As I said, particularly when you add RDS Proxy on top, I'll talk more about that. You get really what I call zero downtime scaling operations with Aurora and Proxy. So as I said, when we were kind of in the middle of migration, we were having issues. We have a very high connection environment, a lot of different applications. It's kind of very frenetic. It was causing problems for EC2, and it caused problems for Aurora standalone. So RDS Proxy was not on our radar initially, and then once we realized we needed to address this issue to complete the migration, we looked at it, and it was a natural fit. And this graph, once again, this is all of our proxies and all of our databases just kind of on single graphs here. But you can see kind of the story where the top is proxy kind of taking on connection load. This is very cyclical, like overnight type job load, hitting 15, 20,000 connections, and the databases below just completely flat. It's not even a bother for them, and the performance is great of the databases because they're not responding to connection requests. Basically, connection is completely stable. I can go into one of the databases, look at the process list, and just see idle connections. Proxy is just holding them, waiting for the load to come. We've seen some very high connection compression, up to 10 to 1, and it works very well for that multiple schema model. As I said, we've consolidated schemas, and this was using proxy was the only way we were able to do that. So it was a very good part of that model. And as I mentioned, the graceful failover when RDS Proxy is on top of Aurora, you get kind of special features where proxy will wait for a new writer to be established in failover operation, so you get very little application impact. So monitoring, so coming from a homegrown environment, we had stats-D agents. We use, so these pictures are all from VMware's Wavefront platform, also known as Tanzu Observability. So that has a plugin for CloudWatch. So all of our data is now coming from CloudWatch. You can build, if you have tools that use CloudWatch data, or you can build dashboards in CloudWatch. So it's very easy for us to use this tool. So we can build very nice dashboards, and we're seeing here just a bunch of different metrics. You get very detailed metrics with Aurora, what's going on with all the different CPU memory and various stats in the engine. We'll take a look, get a little demo of that. All your logs going to CloudWatch, once again, coming from a homegrown solution, roll your own. We didn't have to do any more log management, and I'll mention Lambda is actually an important part of this solution as well. With Chef-based homegrown EC2 MySQL, we have things like init scripts. So with Lambda, we can do some kind of fleet operations. We can catch failover events, things like that. So Lambda has actually been an important part of this solution as well. As I said, replacing a lot of things that you'd run on localhost in a homegrown environment. And then on the left there, I'm sure everyone's familiar with PagerDuty. Very easy to connect your Slack and your PagerDuty for it's a high CPU event. So Performance Insights, which Anu mentioned, is a tool you get with the RDS stack that just comes along. This has also been a great tool for us. Before, we had dabbled with kind of Percona tools and things like that. This is just gives you a great tool right in the RDS console, the single pane approach for all sorts of instance metrics, engine metrics, and then you can kind of deep dive in the SQL as well. Very easy to identify problematic queries. You get full text, and particularly in multi-tenant, you have to make scaling decisions. This gives us a lot of insight. It's very easy to use, and we can have developers on other teams get access to it if they need to debug something where we don't have to manage really anything ourselves. So I have just a little demo video of kind of a bit of a monitoring workflow. How we would use the two tools. So this is give you an idea of a main dashboard. So this is Wavefront or Tanzu Observability, VMware. So this gives you, I might on a daily basis kind of take a look at this dashboard, which has this is all the clusters right now. So this is just kind of superimposed, and could be looking for any anomalies, any spikes, things like that. And then we have the ability to easily. So I'm looking, we can look at, for example, Aurora differences between writer nodes, reader node CPU, things like that. So I may see a spike that I'm interested in. I can see what cluster it's on, drill down, and kind of where this leads to is we have something we now want to really look at what's kind of causing the spike, what kind of SQL. So I flip over to, so this is now Performance Insights in the AWS console. Once again, I can easily just kind of flip through all my databases, select the one that I'm looking for. So I want to match now that with what I saw in our kind of main dashboarding system. So just change the time range, and I see the spike there, can focus in on it and look exactly what's going on, and then Performance Insights lets you then easily look at any of the factors involved in that, so I can actually now look at the SQL that is involved in that spike, and then we can take it back to the application teams or understand why this spike was happening. And in this is a multi-database, so I can look at actually multiple databases in the cluster, multiple users. It's just a very, very powerful tool for that you get with the stack. I think that's it. So kind of just, let's look at like a performance summary. So once again, a lot of graphs of all of our clusters superimposed, just to give an idea. The top is actually showing the results at caching, which is a great feature of Aurora as well. But at the end of with the beginning of the project, we did some benchmarking, but it's very hard to replicate in a production environment, right, with benchmarking, and we have a very busy environment. So we kind of made some guesses. We wound up really impressed in the performance in the end. So if we talk about the wholesale replacement at the end of the project, we wound up with just under 2,000 G6 R6G Graviton processors replaced over 5,000 C5s CPUs. So we had a 64% reduction in CPU. So even when you take the fact that read replicas that were sitting idle, we still came out better. So it was a huge reduction in the amount of infrastructure. We actually, 62 Aurora clusters is our final count. And then with the schema consolidation, we wound up with 7 times the number of customers now on a cluster compared to a single community MySQL. So where we were about 200 at resource limits, we're now pushing easily 1,500 on a cluster. Faster writes with Aurora, we see much fewer locking issues. We have some big roll-up operations, things like that used to cause problems on a community MySQL. It's not an issue anymore. Very fast DDL changes, so index adds, column adds on very large tables, so much faster, allows us much more velocity in database migrations, development pipeline, and I mentioned query cache. It's a really good feature of Aurora that just works. And in our heavy read environment, a lot of reference data, we see about 40%. You can see in the top graph there across all our clusters, probably an average. We did do some tuning. We use the standard RDS parameter groups in our provisioning system. We have a way to create parameter groups for each of our clusters that allows us to test changes. And that's worked very well as part of our Terraform-based provisioning. And then the read replicas, as Anu mentioned, they're working for you, and then they also handle failover. So there is an issue with the writer, reader will take over. So there's no wasted resource, no underutilized resources. Everything is working for you in this environment. So kind of just like sum up where we are, kind of architecture now. So we went from those 166 MySQL shards to 62 Aurora clusters. Most have three of the original schemas on them. We still maintain a few single tenant clusters for some of our largest customers. They're very performance sensitive. As I said, we have a very wide application environment, over 300 auto scaling groups, what we call our classic environment. That includes like our website, things like that. And then we also do a lot of data processing in the EMR. We at any given time, probably about 400 EMR clusters running, and we've been doing a lot of, and our newer development is all Kubernetes, and current environment, probably about 6,000 pods. So RDS Proxy really supports all of that for us. And I'd say at any given time, I'd estimate probably about 10,000 connections. As I said, we are now exceeding 1,500 customers per shard or its Aurora cluster, and we have room to scale. So since we did the migration, we have not added any new clusters. It's still the original count, where before we were adding, a few every month. So kind of at the end, operations. So it's been a huge savings in terms of people. So DevOps team, which manages this in our organization, none of the maintenance operations that we were doing with the EC2, they've all gone away. And people are now working on much more, not on putting up fires and maintaining databases, can work on strategic projects, building new environments, and improving deployment pipelines, like very useful things. We got rid of all the old chef code that was behind all that MySQL, and replaced it with a much more modern stack that's easier for people to get their head around. Terraform, CloudFormation, and Lambda, and as I said, it's really reliable and quiet. We can go weeks without really any alerts, any CPU issues. So it's really been quite the transformation. And the cost is also, once again, going in, we were unclear exactly what kind of consolidation factor we'd get, and the R6, the Graviton CPUs cost more than C5s. But what we found is with the performance improvements and the consolidation, the costs, we actually save money. So this graph is showing kind of over 2021, the cost of the project timeline. Blue is our EC2 infrastructure costs. Red is Aurora, including proxy. We had some ups and downs during the project life cycle with RIs and things like that, but you can kind of see the end result was about 20% total savings. And the savings have been just growing over time, where if we still had EC2, we'd be still expanding all the time, and now we haven't really expanded at all, just a few scaling, adding some readers and doing some upsizing, but as I said, the number of clusters has stayed the same. So kind of key learnings, kind of sum this up. A lot of knowledge building in the beginning of the project. Aurora does have some differences with Community MySQL. As I said, we got very good support from AWS, deep dives, training, and when we got further in the project and we needed help, our technical account management team is very responsive and got us hooked up with some service teams to get deeper insights into what's going on, got us some bug fixes. Aurora and RDS Proxy is a great pair if you have a high connection environment. Works very well, plus having Proxy just on top of Aurora with smooth failover operations and things like that makes it really good for zero downtime operations. The performance, we exceeded expectations. As I said, the performance has been fantastic, and it's good, if you're coming in, you want to take advantage of Aurora features, take advantage of read clustering, understanding how your applications fit into that model. We're not using any fancy query routing technology, but we do have a lot of code that's very heavy on reads and not a lot of transactionality, and it was just very easy for us to point a lot of that stuff at the readers, which made it very, very easy to move, load, and take advantage of that. And then just a couple wish list items. When you do run RDS Proxy, you lose client host visibility down in the database as your process list will show you the proxy hosts for debugging some issues. That has been a little challenge. I was talking to an RDS Proxy product manager today about getting that feature. And then Performance Insights is a great tool, but I'd love to see it tailored a little bit for Aurora with just kind of a cluster view and be able to distinguish between readers and writers. So that was our Aurora journey. I just want to thank AWS for inviting me to speak here. It's been an honor, and my VMware colleagues who supported this year-long project. It was, it came out very well in the end, but it was a very challenging project at times, as you can imagine, but it's been transformative for our organization. So.
All right, thank you so much for joining us. Please don't forget to do the survey for this session. Peter and I will stay around. We have 10 minutes or so if you have any questions, please do come up to us. Happy to chat about it. Thank you so much, everyone.